This is our final lesson covering relationships between quantitative variables, and we'll cover section 3.4 and 3.5. So section 3.4 discusses regression and correlation difficulties and disasters. Basically, statistics done wrong, mistakes that you can make that cause misleading regression and correlation results. So the first thing that can go wrong is you can extrapolate too far beyond the observed range of x values. So what this is trying to do is trying to predict too far away from the stuff that you used to make your line in the first place. For example, back in the 90s, when President Bill Clinton left office, the national debt was on track to be paid off. Go ahead and laugh now, this is hilarious. And what happened is they extrapolated, they said, okay, we have surpluses now, so therefore we think we're going to pay the national debt off at, a rate of blah dollars per year, and therefore we'll be done by this day. But that doesn't take into account unforeseen circumstances like wars or increases in spending. So an example would be things like predicting national debt payoff. Another example could be allowing outliers to overly influence the results. So maybe there's a reason to justify removing some outlier, maybe not. Another example could be combining groups inappropriately. A good example there happens when you combine men and women. We'll see an example in this lesson where when men and women are combined into one group, there appears to be a relationship, but when you separate them out into two groups, there just isn't one at all. And then another problem is if you try to use correlation and a straight line relationship to describe curvilinear data. So for example, temperature in Fairbanks. If you tried to use a straight line equation, you're going to get a correlation coefficient of 0, even though there is definitely a high level of relationship there. So first, extrapolation and interpolation. So extrapolation is using a regression line, a regression equation, to predict values outside the range of the observed data. So that's called extrapolation. Interpolation. This is when we use y values, we find y values or estimate them for new values of x that were not in the original data set, but are within the range of values covered in the data set. So suppose we had temperatures, and we had temperatures for years 1990 to 2010, and we had them at 2-year increments, 92, 94, etc., up until 2010. So extrapolation is going outside of the realm of that data, so going to 2020, for example. Interpolation, since I only had even years, would be picking like a year in the middle, like 91, and predicting the temperature in that year using the regression equation. So interpolation is inside, extrapolation is outside. And if you go it's okay to go a little bit outside of your data set, but going too far outside of your data set can cause problems. And what is too far depends on the situation. The media loves to do this. For example, an article in the Sacramento Bee noted that Americans are just too fat, and researchers say with 54% of all adults heavier than is healthy. And if this trend continues, experts say that virtually every single US adult will be overweight. This prediction is based on extrapolation, which assumes the current rate of increase will continue indefinitely. Is that a reasonable assumption? Do you agree with this? Are we destined to be like the things and people in Wall-E and live on these little scooters that move us around from soda machine to soda machine in virtual reality? And the answer is probably, well, no. This is not a reasonable assumption. And I think it's quite likely that this rate will slow. So the rate of increase of obesity or overweightness is either likely to level off or possibly even decrease, which I think actually has been observed in recent years. Now let's actually look at extrapolation with some numbers. So we have a regression equation that relates the putting distance to success rate in a percent for professional golfers, and it's given by this equation. The success rate is 76.5 minus 3.95 times the distance they are from the hole. And this equation was based on observations of distances ranging from 5 to 15 feet. And the reason the researchers may have looked at those values only is maybe values outside of this made it so that the data wasn't a straight line anymore. And so they just chose to look at the middle chunk where there appeared to be a straight line relationship. So use this equation to predict success rate at a distance of 2 feet and for a distance of 20 feet. And notice that both of those are outside the range of data, but they're not so far outside the range of data, but some weird stuff's going to happen. So y prime of 2 is 76.5, or y hat of 2, excuse me, minus 3.95 times 2, which comes out to be 68.6. Remember, this already is a percent, so just put a percent sign on it. And I don't know, if you're 2 feet away and you're a professional golfer, you're just making 68% of your putts, I mean, I might not even suck that bad at golf. So my thing is that this seems like a low success rate for a really close distance. And y hat of 20 is even weirder. 76.5 minus 3.95 times 20 gives us negative 2.5%. What? So if you're 20 feet away, which I know is like, kind of far, they all of a sudden make negative putts? Like, do they have to give back like holes that they did on previous holes? Obviously something is kind of going on here. So the original data included values beyond those used to find the regression equation. And at a distance of 2 feet, the observed success rate of 93.3%, and at a distance of 20 feet, 15.8% of observed putts were successful. Compare your results from Part A to these observed success rates, and utilize your results from Part A to explain why it is not a good idea to use a regression equation to predict information beyond the range of values used to find the equation in the first place. And so I would say that the regression equation does a poor job on both sides. So the regression equation does a poor job outside the 5 to 15 range. It seriously underestimates success. So it underestimates by almost 25% at x equals 2 feet and gives a crazy answer at x equals 20 feet. So lesson learned, extrapolate with caution. So here we have a regression equation relating student height, and this is actually for female students, and father's height, and I said that later. So we found this using 10 female students, and the equation was y hat is 19.42 plus 0.658. So give the value of the y-intercept Does it have a meaningful interpretation in this situation? Explain. So the y-intercept, beta naught, is 19.42. So this tells us that when x equals 0, y hat is equal to 19.42. In other words, if x, which is a father's height, if the father's height is 0 inches, the daughter's height is 19.42 inches. Okay, so obviously this makes no sense. You cannot have a 0-inch tall father, and probably 19.42 inches. Ooh, you know, that's less than 2 feet. I don't know what the shortest human on record is, but my suspicion is that they're probably bigger than that. Give the value of the slope and interpret what it means in this situation. So the slope, m or b1, is 0.658. And recall that that's delta y over delta x. Now y is the student height. X is the father's height. So if father's height goes up by 1, so if a father's height increases by 1 inch, height of daughter student increases 0.658 inches. Magic words, on average. In this class, the magic words are on average. When you were 5, it was please. So for every 1 inch increase in father's height, we see about a 0.658 increase in the height of the daughter. So use the equation to predict the height of a female student whose father is 70 inches tall. So if you know the dad is 70 inches tall, what do you expect the daughter's height to be, approximately, on average? So plug in 70 for x, and we have that this is about 65.48 inches. So one student we found was 67 inches tall, and her father was 70 inches tall. Find the residual for this student and explain what it tells you about his student in relation to the other female students whose fathers are also 70 inches tall. So the residual, recall this is y minus y hat. And in this case, the y is 67 because that was an actual measurement. Minus from the previous part of this problem, 65.48, that's the predicted value, 1.52. And just think the 65.48 from the previous part was the average. Is this person above or below average? And the answer is above. So this student is 1.52 inches taller than other students, and it isn't all other students, it's other students whose dads have the same height. So 1.52 inches taller than other students with fathers who are 70 inches tall. She's probably shorter than students who have fathers significantly or even a little bit taller than hers. Now, would it make sense to use this regression equation to predict the height of a male student whose father is 70 inches tall? Well, the answer is no. You used female students to make the equations, and one would suspect that the relationship between fathers and sons actually is a little bit different. So no, the data used to make the equation came from female students cannot apply to male students. This type of thing happens in like medicine, or at least used to happen quite a bit, that studies were done on men and not on women, and so there was extrapolation to women based on data collected for men only, which has caused problems. Now, here's an regression equation that relates the ideal weight to the actual weight for men and women. And these equations have kind of interesting properties. Like for women, an actual weight of 110 corresponds to that also being the ideal weight. And so the same thing is true for a certain weight for men. So now the question is let's predict the ideal weight for a man who weighs 140 pounds and for a woman who weighs 140 pounds, and we'll compare the results. So ladies first, the woman's ideal weight at 140, that's going to be 44 plus 0.6 times 140, which is 128. So if a woman weighs 140 pounds, she wants to weigh 128. And for men, it's 53 plus 0.7 times 140, which is 151. So what this tells us is that on average, women who weigh 140 pounds would like to weigh less. Let's say weigh about 12 pounds less. And men who are 140 pounds want to weigh 11 pounds more. And the specifics of this relationship, they're due to the fact that we actually used 140 to plug in for the actual weights. And that should make sense that women who weigh 140 typically probably would like to weigh a little less. Not all of them, but some of them. And men who weigh 140, that's pretty small for a guy. They probably would like to be a bit heavier and be more beefy or muscly. Does the intercept, or do the intercepts have logical physical interpretation in this context? I'd say no. Both give the ideal weight if the actual weight is 0. Of course, that makes no sense. And do the slopes have a logical interpretation? Explain. So yes, I think they do. We'll just look at the women's. So for women, the slope is 0.6. And this means that if the actual weight increases by 1, ideal weight increases by 0.6 pounds. The interpretation is almost the exact same for the guys, except for it's going to be 0.7 pounds. Now, sometimes there are influential observations, and what these are observations that change the direction or the strength of the relationship. Okay, so a really good example of this looks at earthquake intensity and the number of fatalities that occurred. So earthquakes that occurred in the continental US. In the table below, we have all the major earthquakes that occurred in the US that were at least a magnitude of 7.0 and or which there were at least 20 fatalities. The correlation between deaths and magnitude is 0.26. However, if the one sort of semi-obvious outlier is left out, then the correlation is negative 0.824, as in a lot better, which indicates that fewer deaths are associated with a greater magnitude. Why might this correlation actually be negative? So first of all, that one that we threw out was the 1906 San Francisco earthquake. And you can see from the picture that, there definitely is sort of a downward trend among these points, but having this point up there pulls the regression line's slope to being a positive number. So this is the data with that point removed, sort of zoomed in, and you can see there's definitely some kind of negative-ish pattern going on there. So the problem really might be is that these really big earthquakes don't tend to happen in very populated places. So one problem may be that earthquakes don't happen only in populated places. I mean, they left out Alaska here probably for obvious reason because it was going to destroy the relationship, and lots of earthquakes here. But magnitude of 7.0 or higher, and or there were that many fatalities, you could have lots of high magnitude earthquakes, but they occurred someplace where there weren't a lot of people, like the West Coast and the mountains, and of course there were not many fatalities, if any, then. And another problem might be better technology. And the time of occurrence. I mean, who knows? Maybe there was better technology, and that's why this earthquake was so bad, because the technology in 1906 was not able to withstand that kind of blow. So it's not clear, but it is clear that removing that data point seems to produce a regression line that fits the data a lot better, and therefore you might be able to justify throwing it out. Next, we have an example of inappropriately combining groups. So height and lead feet. For a sample of college students, a scatter plot of their height and what is the fastest you have ever driven a car? That was a question that was asked of them. Is shown below. In the original scatter plot, there's a modest correlation coefficient of 0.39. That's not great, but it's not bad. So there seems to be an upward trend. As your feet get bigger, you just can't keep them off that gas pedal. You just push down and go faster. But when you separate out men and women, the correlation just completely goes away. So with women, the correlation coefficient is just 0.04, men negative 0.01, which effectively is saying that we really have things that are slope zero here. And what you can see is when you put these things together, the men end up kind of being above and to the right of the women, which makes it appear as if there's an upward trend because men tend to be taller. And that's what's going on, is that men are taller and also tend to drive faster. So it can be hard to figure out, okay, how should I separate these subgroups out to see if this kind of problem is happening? But, really common thing to look at is take men and women and look at them separately. And then curvilinear data, it's really, really, really important to look at a scatter plot before you find a regression line, because that's how you can tell if a regression line, as in a straight line, is a reasonable thing to do in the first place. So here we go. We have a graph that looks at the population of the US for each census year between 1790, holy cow, and 2000. And you can see that there's this really beautiful, nice, exponential looking curve here that's pretty perfect. And if we looked at that and if we didn't look at this and just naively use software to fit a regression line, what we're going to get is this. So there's your straight line. And you can see that the line does a pretty crappy job estimating the populations at any given time except for this one and this one. So look at how back in 1790 it underestimates the population, and for 2030 the estimates are 269 million versus 363.5 million. And you can see that this one seems to certainly be much, much, much better with match the pattern with what's going on with that point, much more so than this one does. That would require this to change direction suddenly, which probably isn't going to happen. So the moral of the story is to graph your line or data. Moral of story: plot points, look at the scatter plot. So look at the scatter plot before you assume it's linear. So plot roughly what happens to temperature here in Fairbanks over the course of a year. So say taking all the Januaries, all the Februaries, all the Marches, all the Aprils and plotting them. Okay, so January temperatures probably below, hovering around 0. They go up. They peak sometime June, July. Then they go down, and by December they're back where they began in January. So roughly you're going to look something like this. If you try to fit a regression line, as in a straight line, it's going to give you slope 0, even though there really is like a nice predictive pattern there. So if we assumed it was a linear relationship, we're going to get R about equal to 0. It's just what's going to happen. No, there really is a relationship. It's just not linear. That's all. And the final lesson to really, really hammer home is that just because two things are correlated, it does not mean that one causes the other. Correlation does not prove causation. So, for example, weekly sales for flu medicine, this increases with weekly coat sales, even though the two variables have nothing to do with each other. But if you were to graph them, flu med coats, it's going to tend to be a positive association. And the question is, well, why is that? Well, flu incidence goes up in the winter as does coat purchasing. That's why. People who use vitamin supplements get fewer colds than people who don't. So a really common thing to conclude here is, well, maybe vitamin supplements mean that I get sick less often. And while that might be the case, this has been a problem in health studies before, that you don't know if those people taking vitamin supplements are just more healthy overall. So this is something called healthy user bias. And what this states is that people, at least in this example, people who take vitamins may be more healthy overall and therefore get fewer colds. So just the way it works. They could also be wealthier and maybe they're able to get more sleep or they work less hours. But in general, it's not, you can't say that those supplements cause the fewer colds unless you divide people up into two groups, give half the supplements, don't give half the supplements, and look and see what happens to them. And a real example happened in the 90s. There was a survey done of nurses, and they found there was a link between supplemental estrogen taken after menopause and breast cancer. As in, breast cancer went, in that case, it went down. But when they did an actual study and they took people and put them in two groups and they gave some estrogen and they gave some a placebo, they found that people who took estrogen actually had an elevated risk of breast cancer. And what was present in that study as well was the same thing, healthy user bias. People that were taking estrogen in the 90s were taking it because they thought it was healthy, and they tended to smoke less, drink less, eat less, exercise more, and all of those things made it appear as if the estrogen was causing a lower rate in breast cancer when it actually wasn't. So suppose you find an association, and what are the interpretations of its association that you could make? So if you want to establish causation and not just correlation, you have to do a randomized experiment. So you must collect data using what's called a randomized experiment. As in, you assign participants completely randomly to get we'll say treatment. And that treatment could be that they say get an actual drug or get a placebo, or they get one of two drugs or a placebo. But the point is you assign them randomly. And I do mean you, the researcher, not the people pick themselves. So if you want to establish causation, you have to do it this way. And this is one reason that smoking has never ever actually been proven to cause lung cancer, because we never actually did a study and said, okay, half of you are going to smoke cigarettes for the next 10 years and half of you aren't, because that was deemed an unethical experiment. So technically that's never been proved causally, but the strength of that correlation coefficient is so high, it just seems like the relative risk is so high, it just seems as if smoking is the only plausible explanation. So there are at least 4 possible interpretations of an observed association between the explanatory variable and a response variable. The first one is that there might be causation. So the explanatory variable is causing a change in the response variable. Remember, this can only be concluded if you do a randomized experiment. and may not be concluded from a survey. There might be causation, but confounding factors make the causation difficult to prove. So a confounding variable is a variable that is not the main concern of your study, but it might be partially responsible for the results. For example, does lack of exercise lead to weight gain? And a possible confounder there would be diet or stress. Another thing could be that there's no causation. The observed relationship can be explained by how one or more variables affect both the explanatory and the response. For example, we have coffee drinking and cancer. So it was thought that coffee drinking led to cancer. And so coffee drinkers around the world were very sad because they're like, oh my goodness, this caffeine habit's gonna kill me. But when they controlled for smoking, so smoking was affecting both the cancer rate and related to that coffee drinking, they found that the incidence of cancer in the non-smoking group, but coffee drinking, was actually lower than the non-smokers who didn't drink coffee. So yay, have your Java. And the final thing is that the response variable could be causing a change in the explanatory, as in it's not clear which way the relationship is working. So for example, does regular church attendance, does this lead to better health? Or is it vice versa? Does better health lead to regular church attendance? Another place this has been suggested is, does lethargy, as in being lazy, does this lead to obesity? And a lot of us have thought for a long time that, yeah, if you're lazy, you're gonna be overweight or obese, but maybe being obese makes you more liable to just not feel like very energetic, and maybe it's obesity causing the lethargy. We just are not sure. It might actually go the other way. So, final thing, one more scatter plot drawn in Excel. So we have the US Census Bureau, and it estimates the average number of persons per household in the US for census years between 1850 and 2000. So look back long ago in 1850, there were like 5.5 people per household. Compared that to 2000 when it's down to just above 3. So here is the scatter plot, and I drew this in Excel. Is the relationship linear or curvilinear? It appears to be mostly linear. Is the association between persons per household and year positive or negative? Definitely negative. Next, on your scatter plot, add in a line that you believe fits the data. So draw in what you think is a pretty reasonable regression line that goes through the points as best you can get. And use this to average the number of estimate the average number of persons per household in 2010. That's right here. So somewhere in between 2 and 3 and on the low side of 2. So about, we'll say 2.3 persons per household in 2010. And you can see that since, that's not super far outside your range of data. I mean, 10 years past 2000 when you have a data set from 1850 to 2000 is not very far out. So probably that's going to continue. Although you did see the sort of leveling off pattern here that maybe that wouldn't go down quite so much. So that's it for chapter 3.